Hello, welcome to my office, also to my video on finding absolute extrema. So we've looked at local extrema, local maxima, and local minima. You know, a function like this, some sort of fourth degree polynomial, this probably is. It goes up, it has a local max, it comes down, it goes up, it has another local max, it goes down. Okay. And we sort of made the observation already. I mean, the reason we use the word local is that this first local max is only a maximum if you cover up a lot of the graph and only look at this part. Otherwise, it's not a maximum. You see, we get above it around here. So in this video, we'll talk about absolute extrema, sort of genuine maximum and minimum values. If I have this curve, that in terms of absolute extrema, there's an absolute maximum. And this value over here is not an absolute maximum. It's a local maximum, but it's not absolute because we do get above it. And if we think of the curve that I've drawn, go up, go down, go up, go down, if we think of this as being the entire function, then there's also an absolute minimum. And notice that the absolute maximum and the absolute minimum are occurring in very different contexts, you might say. This absolute maximum is also a local maximum. It is occurring at a critical value. The derivative is equal to 0. The absolute minimum is not occurring at a critical value. The derivative is not 0. Whatever the slope of this tangent line is, it is not 0. So finding absolute extrema requires a little thought because they're not always local extrema and they don't have to occur at critical values. Again, the absolute max did occur at a critical value, but the absolute min didn't. So we're going to, at least for this section, we're going to look at a special situation where we're looking at a function on a closed interval from A to B. So including A, including B, and of course including all the values between A and B. In such a situation, if the function is continuous on such an interval, the absolute extrema, both a max and a min exist. That's a theorem of calculus. It's the extreme value theorem, although I don't think your textbook ever gives you that phrase. And these absolute extrema can only occur at critical values or endpoints. Returning to this example, so we've got a closed interval from A to B. The absolute max occurred at a critical value. The absolute minimum occurred at B. It occurred at an endpoint. And even though it seems like it should be quite similar, the way we find absolute extrema is quite distinct from the way we find local extrema. That being said, the first step will be the same. The first step will be to find critical values. So let's say f of x equals x cubed minus 2x squared plus x plus 1. And we're on a closed interval from -1 to 3. Let's see how we find the absolute extrema. So step 1 is going to be the same. We're going to find the critical values. The derivative always exists. So the critical values are just what we get by setting it equal to 0. Um, this thing factors, I think. Um, my My secret shame is that I'm quite bad at factoring. I'm just going to hit it with the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a, 4 plus or minus 16 minus 12 is 4. The square root of 4 is 2. Okay, this wouldn't have factored easily after all. We do get 1, just a very nice root, and then we get a fraction. 4 minus 2 is 2, 2 divided by 6 is 1/3. So these are our critical values, and we observe that these are in the interval we're looking at. If they weren't, we just discard any that weren't, but they are. And I've made this statement that these absolute extrema can only occur at critical values or the endpoints. So we have two critical values, 1 1/3. We have two endpoints, -1 and 3. Let me see. -1, 1/3, 1, and 3. And now instead of mucking around with the first derivative test, we're going to create a table. The first derivative test, well, there are a few reasons we're not using it. The first derivative test tells us if something's a local extrema, but that's not what we're looking for. Also, the first derivative test only applies to critical values. It's useless at the endpoints. Instead, we're just going to make a table. I mean, we've got this function, x cubed minus 2x squared plus x plus 1. And this function achieves a maximum value and it achieves a minimum value. So we're just going to take these numbers, -1, 1/3, 1, and 3, and we're going to plug them into this function. I will do this off camera. Notice that, we're not creating a sign chart. In particular, we're not using the derivative for this step. We're plugging the numbers into the original function. And we ask, okay, so what's the absolute maximum? This function has a maximum value. That's the extreme value theorem. The maximum value occurs at one of these four values. And we just say, well, is the maximum value going to be -3? Is it going to be 1.148? Is it going to be 1? Or is it going to be 13? Which of those values is the maximum value? Of course, it's 13. The absolute maximum occurs at the point 3, 13. What about the absolute minimum? We know it has one. We know it's one of these four values. Of these numbers, -3, 1.14, I guess 1.15, 1, and 13, which of these numbers is the minimum? Well, -3. So the absolute minimum is occurring at -1, -3. And visually oriented learners can check that answer by looking at the graph. Here's the function from -1 to +3. We see it does start at -1, -3. Then it goes up. Here's the 1/3. It's a critical value, but it's not an absolute extrema. It goes down. Here's the 1. Again, it's a critical value. It's not an absolute extrema, though, because then the graph goes up and achieves its maximum value at 3, 13. So we can look at this graph and verify our answer. This is the minimum value. This is the maximum value.